We have been talking about heaps in the last few videos. We looked at a process called Heapify, where we take in a list, do some swaps within the list, and convert that list into a heap. It could be a min heap or a max heap. In Python, using heapq.heapify, we always create a min heap. We also saw that the complexity of Heapify process is order of n, which I thought is a very interesting result. So I thought at this point of time, let's sort of stay, sort of pause here for a moment and look at how does this compare, let's say, with sorting and say min finding. In the last lesson, we looked at basic sorting algorithms, bubble sort, insertion sort, selection sort, and we argued that all of them have complexity of order of n square. In fact, we saw this in action by profiling the runtimes. So clearly, we can see that heapifying is order of n, much simpler than sorting using, let's say, selection sort, insertion sort, and bubble sort, which seems to make sense, because we are doing very few comparisons in heapification compared to, let's say, sorting. Now, more advanced sorting algorithms get us to complexity of n log n. Interesting to note here that heaps themselves lead to an algorithm called heap sort. We are going to learn that later, whose complexity is order of n log n. N log n is definitely better than n square, but still it's worse than n. So in short, the process of heapification is in fact significantly simpler than sorting the entire list. And the difference is seen more and more as n becomes large, right? So this is something quite interesting. I thought this is something to think about. Why does this happen? Why is it that I need more work to sort an entire list compared to just creating a heap? Well, the way to think about it, let's think about it. Let's take a hint here. Any sorted list, let's say any list sorted in ascending order, is in fact a min heap. How do I know that? Well, look, if I have a sorted list and I impose a complete tree on it, the minimum item will be on the root, and every parent will be, by definition of sorting, smaller than the children, which means that we have a min heap with a sorted list. But the question to ask ourselves is every min heap a fully sorted list? In fact, the answer is no. And we can see an example right here. You notice this list here, 6, 23, 53, 49, is not sorted, but indeed is a min heap, because all we are doing is that at the parent nodes, you're maintaining the sorted, the heap property, which is saying that, okay, the parent should be smaller than the two children. This is a less restrictive condition that's saying that the entire list has to be sorted, which means that, look, to create a heap, we need lesser amount of work. And indeed, then it's no surprise that heapification is a less complex process than sorting. In fact, it's interesting to note that heapifying is same complexity as min finding. So if I have a list of, let's say, n numbers, I want to find the minimum of that, as we were doing, for example, in selection sort. So we end up doing n comparisons to find wherever is the minimum. That complexity turns out is exactly same as heapify, which is very thought-provoking in some sense, because in heapification we are doing comparisons, but because of this tree, we are also doing comparisons, and movements and so on. But because of this tree structure, as we discussed, on the leaf node, nothing to be done. On, let's say, which are maybe majority of nodes, on half of those nodes, perhaps one comparison, one swap. On, let's say, half of those nodes, two comparisons, two swaps. The overall complexity works out same as finding just one min number. So think about it. If I have to convert a list into a heap, it's order of complexity wise, similar to finding the minimum in that list, right? Very interesting result. Having an appreciation of this sort, having a sort of thought process in this direction, helps us choose the right approach for a problem, and that's why I thought it's interesting to make this comparison here. I hope you found this interesting. Do look at our website www.ybyte.in for more such content, and forever enjoy coding. Take care. Thank you so much. Bye bye.